This video is covering basics of cross product. So the cross product of two vectors v and w in R3 is defined to be the vector v cross w equal to magnitude of v times magnitude of w times sine theta times n. Theta is the little angle between v and w. N is the unit vector perpendicular to both v and w, but there are two of those, so use the one given by the right-hand rule. What is the right-hand rule? Point the fingers from your right hand toward v and then curl them toward w. Look at that arrow in the picture. And then your thumb is going to point in the direction of n. This makes I cross j the standard vectors. I cross j equal to k, j cross k equal to I, k cross I equal to j. Now, v and w are parallel, then the angle between them is 0, and sine of 0 is 0. Therefore, v cross w is going to be the 0 vector because it has no magnitude. V cross w is perpendicular to both v and w. V cross w, if you change the order of v and w in the multiplication, is going to be equal to negative w cross v. And that makes sense because by the right-hand rule, your thumb is going to point the opposite direction. Magnitude of v cross w is the area of parallelogram with sides v and w. Look at the parallelogram. Here's v, here's w. Then I put in another vector v to the, so it follows w, another vector w to follows v. That makes a parallelogram. And in that parallelogram, the base is the magnitude of w. The height is magnitude of v times sine theta, sine of angle in between. Multiply those two together to get the area of the parallelogram. But this is also the magnitude of the cross product. Now, if you want to find the cross product of two vectors in R2, treat them as a vector in R3. So if you have a vector v equal to v1 and v2, instead of writing it like that, write it as v1, v2, and 0. And same thing for w. They're kind of equivalent because v1 and v2 it can be considered as a vector in the xy plane, and therefore in xy plane your z value is going to be 0. In this case, v cross w will always be multiple of k. That is 0, 0, and 1. The k, the standard vector. Now let's talk about how to find the formula. So we do a basic case and we leave the more complicated case up to you. And the basic case is, let's compute the area of the parallelogram formed between two vectors, v and w. If I can compute the area, then I can relate that to the cross product, because cross product, the magnitude of cross product is that area. So look at the v and w in here. Form a parallelogram over it. I'm putting the axes in. And I'm considering only in the 2D situation. Now, this reminds me of sum of two vectors. So I put in the vector of the sum. Now, That vector of sum divided the parallelogram into two pieces, two triangles. If I compute one of those area of one of those triangles, I can multiply that by 2 and get the entire area. So I start with the yellow area in here. That yellow area, I drop down a perpendicular over here. It forms a little triangle over there, and I drop another perpendicular over there. Look at these two perpendiculars. The first perpendiculars basically is going from the point W1 and W2 to x-axis. The other one goes from the sum vector to the x-axis. Now, looking at that area, the yellow area is equal to the orange area. What is the orange area? Orange area is the perpendicular drop down from the V plus W vector. And so the sides of this triangle are V1 plus W1 and V2 plus W2. Area of a triangle is V1 plus W1 times V2 plus W2 divided by 2. But this is not equal to yellow area. You have to subtract the extras. What are the extras? Extras are this cyan area. Cyan area is kind of complicated. So I'm going to divide it into a triangle and subtract that triangle from the area of the orange. And that triangle, because it's related to the perpendicular drop down from W, is going to be, that area is going to be W1 times W2 divided by 2. Then subtract the trapezoid, the purple trapezoid area, and that is the average of the bases times this height. The height is V1 plus W1 minus V1, which is just V1, and the one base is V2 plus W2, the other one is W2. Now I do have the area, the yellow area, which is half of the parallelogram, entirely connected to components of V and W. If I clean up my algebra, this is the algebra, multiply it by 2, I get this expression. Clean it further, that's homework for you guys, and you end up with the area of the parallelogram be equal to V2 W1 minus V1 W2. Talk about the general area. The computation that we did was specific. Here, if we curl our hand from W to V, thumb points to positive K. According to the definition, W cross V is going to be equal to that K times the magnitude, which magnitude in this case is the area. V2 W1 minus V1 W2. The other presentation for this is the determinant ijk, vector W1, W2, 0, second row. The third row, vector V1, V2, and 0. So determinant of this matrix. This is our sketch of the proof for our formula for the 2D case. What is the general case? Before that, because we just talked about determinant, I want to make sure that we remember the determinant. Determinant of a 2 by 2 matrix is the determinant of, let's say, matrix A, B, C, D, first row A, B, second row C, D, is going to be the diagonal AD minus the off diagonal BC. Determinant of a 3 by 3 matrix can be calculated by decomposing it into linear combination of 2 by 2 matrices. So if you have a matrix with rows A1, A2, A3, then B1, B2, B3, then C1, C2, C3, you can decompose it by A1 minus A2 plus A3, that's the first row. And when you're doing that, when you're using a decomposing over A1, you're going to cover the first column and the first row, and what is left, find the determinant. And for A2, you cover the second column and the first row, and you find the determinant. And for A3 as well. There's a negative sign in here, so because when you're basically expanding the determinants, you change the sign as we go. This is just for the 3x3 matrix. You learn more about determinants in a linear algebra course. Now, cross product formula is going to be, in general, is going to be a determinant of first row ijk, the special vectors, and then the second row vector v, v1, v2, v3, and then the third row w1, w2, w3. Now, this formula enables us to actually compute the cross product versus the definition tells us more about the geometry of the cross product.